Class, we are on to the next section. We're doing chapter 10.3 today. This is matrices and systems of linear equations. So we talked about systems of linear equations so far. We talked about two equations with two variables in larger system. We mainly focus on three equations with three variables. So today we're going to be very general and talk about any size system, and we're going to really hone in on this idea of a matrix. Okay. So every linear system which has this general form. So here we have a11 times a variable x1, a12 times a variable x2, and so forth times a1n times xn equals some number. So just looking at this first equation, the first one here tells us that we're talking about the first equation, right? So this is the first coefficient in the first equation. This is the second coefficient in the first equation. The nth coefficient in the first equation, and then this is what this whole equation equals to for the first equation. So this first number here specifies what equation we are working with. The second number tells us which variable number or which coefficient place we're working with. Okay, so if we have m equations, right, 1, 2 up to m, and there's 1, 2, n variables, our last coefficient would be notated by a with the subscript of a of mn. Okay, so there's m equations, 1, 2, 3 up to m of them, and I have 1, 2, 3 up to n variables. Okay, so what we do is we would take this system of equations. So maybe there's two equations with three variables. Maybe there's 5 equations with only 2 variables, right? It doesn't really matter, but what's going to happen is we take this system and we turn it into a matrix. We call that system, we call that matrix the augmented matrix. And what we're doing is we're only using the coefficients, the a11, the a2n, the b3. We're only using those. We don't need the x1, we don't need x2, we don't need x3. These might not even be x1, x2, x3s. These might be x, y, and z, if there's only 3 of them, for instance. Regardless, we're not using the variables. We're only using the a values, right? Whatever number would be in the a place, and whatever numbers would be in these b places. Okay. So removing the variable terms, it will look more like this. So this ... means that we go on forever. Okay. Notice what happens when I go along the main diagonal, which we talked about a little bit when we were talking about determinants. Those numbers are always the same. 1, 1, 2, 2, and so forth and so forth. The next one here would be 3, 3, and 4, 4, in that nature, right? So again, now that I've gone from equations to a matrix, my numbers represent something a little bit different. If you notice, all the things in this column have 1 for the second number. Right? All the things in this column have 2 for the second number, n for the second number. So the second number actually tells us what column we're in. The first number, again, here was what equation we're working with. Here it tells us what row we're in. The first row, the second row, right? So 2, 2, 2. These are all telling us what row that we're in. So every time we have a system of equations, basically what's happening is that each equation makes up a row, right? So before we're using vectors and we're saying, hey, this vector I'm going to put in this row, like for the cross product or the determinant, for instance. So here, instead of using the vector, we're using the equation. The second equation makes up the second row. Okay. And we disregard the variables. Okay, we're only using the coefficients. So again, when we go this way, this is rows. Right, just like again, if you're going to the theater, you find your row and then you move lengthwise to get there. But the stairs that lead you there, those are a column, right? Up and down is a column. The things that hold up your ceiling are columns. So columns are up and down. Rows are left and right. And remember, we go in order, right? R, C. So when we talk about the size of a matrix, which we'll talk about in a second, we always talk about how many rows or equations first, and then we talk about the number of columns, or the number of variables second. Okay. So its dimension is the number of rows by the number of columns. So as an example, let's say that this is my system of equations. Okay, x1, x2, and x3 are unknowns, they're variables. And I have my coefficients, right? I have 3 equations, 3 variables. So when I put this in an augmented matrix, it'll have 3 rows, but there will be 1, 2, 3, 4 columns because we also have to take the right-hand side of the equal to be its own column. Okay, so putting this into a matrix, I'm only using the coefficients. I'm using the numbers only. So the 2, the negative 3, the 1 here, the 1. If there's something missing, then I use a 0. Okay. If you see no number, it's a 1 because there's only one x1 here. There's only one x2 here. There's only one x3. So 1, 1, 1, 2. Again, if something was missing, like for instance, if this x1 was gone, this would be a 0 right here. I wouldn't just leave it blank or write the first one because this column is reserved for all of the coefficients for the x1s. Okay, this column is for all the coefficients for x2s, and this column is for all of the coefficients that go with x3, and this column is all of the right-hand side entries. Okay, we call each one of these things an entry, very similar to what we do for vectors. These are the components of the matrix, right? Each entry inside of the matrix. So this is a 3x4 augmented matrix because it came from a system of equations. Here you see I use a bar. Here you see I use the 2 dashed lines. It doesn't really matter, but really what it's doing is it's signifying to the reader that I'm separating the left-hand side from the right-hand side of the equation, right? So this line here represents the equal sign. These dashed lines, these I forgot the name of those. They're not semicolons, but they represent the equal sign as well. Okay, so again, I have 3 rows and 1, 2, 3, 4 columns are C, right? Rows and the columns is the order. So we have what are called elementary row operations. These row operations we were just talking about in the last 2 sections, really the last section. Okay, they are operations I'm allowed to do on my matrix that do not change the solution set of this system. So as long as I follow the 3 rules, they're the same 3 rules from the last section. As long as I follow those 3 rules and I do them correctly, the final answer that I can derive from this matrix is the same as the final answer that I can derive from this system of equations. Okay, so just to review, those operations are that I can interchange 2 rows. If I don't like a row for some reason in the place that it is, I can take that row and I can switch its place with any other row. That's just like me swapping out 2 equations, right? If I move this equation to the bottom and I move this one to the top, I didn't do anything. I didn't change anything. So I can do the same thing to my matrix and it won't affect my equation. Now, if I were to switch the variables, right? If I switch the columns, I couldn't do that. But I can switch an entire row. So I can interchange 2 rows. I can multiply a row by a non-zero constant, meaning that I can take a whole row and multiply every number there by 5. That would be the same thing as me taking this entire equation and multiplying it times 5, which is something that we would do when we have fractions, for instance, right? We multiply an entire equation times a number so that I have no more fractions. Or maybe I want the coefficients to match up so I can add them together, okay, to eliminate them, right? So everything we just did in the last section, we're doing now, but instead of doing it to the system of equations, we're going to do it to a matrix, so really just to their numbers. So I can swap rows, I can multiply a whole row, or I can multiply 1 row times a number and then add it to another row. And my goal is going to be the same as it was before. Take the first entry, get all the stuff below 0, come down to the next entry in the next equation, basically, make all the variables below it 0, and so forth to try to get that triangular system. Okay, so we'll talk about that a lot more right now, but let's focus on these 3 row operations and verify that they do represent what we've been talking about from the last section and how it relates to what's going on in our system of equations, right? So let's do an example. So using the same system that we just had, okay, we'll do one of each of these things, and we'll see how it changes their matrix. So let's say we want to exchange two rows. So I have the same equation. This is the notation for swapping rows. It's saying I'm going to take row 1 and I'm going to swap row 2. I'm going to take row 1, I'm going to take row 2, and I'm going to swap their positions. So if I do this with my equations, okay, it will look like this. So what was row 3 is now row 1, I'm sorry. What was row 1 is now row 2. Okay, so I've swapped R1 and R2. These two have switched places. Okay. So if I do this with my matrices, if I swap row 1 and row 2, the first two, instead of 2, negative 3, 1, 1, I would write this, right? 1, 1, 1, 2. So 1, 1, 1, 1, 2, 1, 1, 1, 2 would be on top, and this 2, negative 3, 1, 1 would be in the middle now. So swapping rows 1 and row 2 is this. Okay, very straightforward. I can multiply an entire equation or a row, right? So again, everything here is being done to the equations. The stuff being done here is to the rows by non-zero constant. So if I have this is saying I'm going to take row 3, okay, and I'm going to multiply it times negative 2, right? R3 turns into negative 2 times R3. So I'm going to take this third row, this third equation, I'm going to multiply everything by negative 2. You can see here, I switch signs, and everything is a multiple of 2. So if I do that in terms of a matrix, right, the coefficient matrix, I take this, I'm going to take row 3, and I'm going to multiply everything times negative 2. So this turns into negative 2 plus 4 minus 6 minus 8. It's actually a little bit easier because I have a lot less to write than I do when I have the whole system of equations. Okay. So those are the first two operations, and so the third is to add a multiple of one equation to another. So to do that, this is how I write it. R1 is the one that is changing. Okay. So my R1 now, this equation 1, is going to turn into, I keep this equation the same, and what I'm going to do to it is I'm going to subtract from it 4 times the last equation. So the second equation will remain the same, the last equation will remain the same, but in my new set of equations, the first equation will be changed. Okay, so 2 and 3 stay the same, but my my first equation is different. And what I did to get this new equation, right? So again, R1 is the one that's changing. What am I doing to it? I'm going to take it and I'm going to subtract 4 times the third row or third equation to get it. So generally when we're talking about the row that we're changing, we say this is the one that I'm going to change. I'm going to take it and then I'm going to do this thing to it. Okay. So here we have same thing. I'm going to take R1. Okay. That's the one that's going to change. And what am I going to do to it? I'm going to take it and then I'm going to subtract 4 times the third row from it. So I'll have 2 minus 4, which is a negative 2 now. I have negative 3 minus a negative 8, so that'll really be plus 8, so that's why we get 5. I'll have 1 minus 12, negative 11, and then 1 minus 16, so negative 15, and everything stays the same. So those are 3 row operations, our elementary row operations, and the different notations. Okay, so really be familiar with the notations, because every time we do something in this section, we have to write the notation. It allows the reader to know what it is that you did from one matrix to the next. Okay, so again, we're operating on the first row. So row 1 remains unchanged, and what we're doing is we're adding a multiple to it, right? So that's why we say row 1 becomes leaving it alone and then manipulating it in this fashion. So then we write the end result. Okay. To solve a system of equations, what we're going to do is we take our system of equations, we turn it into an augmented matrix. Okay. We use our 3 elementary row operations, the 3 we just went over: swapping rows, multiplying a row by a constant, and adding a multiple of one row to another. And we do that until we can reduce it down to a triangular matrix. Okay, so this process is called Gaussian elimination, which we are somewhat familiar with from working with just a system of equations. Once we are in what is called our row echelon form, then we can use our backward substitution just like we did before. Okay, so we're going to be going kind of back and forth. We're going to start with a system of equations, put it into an augmented matrix, do what we need to do, right? Get into the form that we want, and then go back into a system of equations and use our backward substitution, right? So you guys are familiar with this. What it does is it cuts down on the amount of writing that we have to do. It keeps everything nice and compact. And it's very helpful when we have larger systems. This is the way that your computers solve systems of equations, how they work with photos, how they open the apps on your phone, all these kinds of things, right? So this process is a very, very important process, which we use quite a bit once we get into a deep study of matrices. Okay, so let's talk about Gaussian elimination. I know that we're somewhat familiar with it because we covered it last section, but let's cover it one more time, especially under the guise of a matrix, so that we're familiar with how to do this. Okay, so really our goal is it's a process. It's what's called an algorithm. Okay, what we want to do is we take our augmented matrix. Okay, here I wrote X everywhere because it doesn't really matter what the values are. These are all numbers. So you see how I'm not really specifying the size, which is why we have these dots. It could be a 2 by 2. It could be, 100 by 100. It could be like 2 by 300 in size. It doesn't really matter what the size is. Okay, we have our augmented matrix. We have a bunch of numbers in here. We have our line that separates our left-hand side from our right-hand side. This is, again, equal to our equal sign. Okay, so my goal is I want to first make the first number here 1. Okay, the first entry should be 1. Now, in order to do that, there's lots of ways to do it. Most people will probably think that, oh, I just take whatever number is already here. Let's say it was 12, and I'll just divide everything by 12 because I can divide a whole equation. Now, the problem with that is, yeah, that might be nice because now you have a 1 here, but now everything else is a fraction. Okay, and then once you introduce fractions, you have to do a fraction. So really the goal is to try to not to divide everything by one number, the whole row by a number if you can, unless, for instance, everything is a multiple of 2. Yeah, divide everything by 2. That's great. Okay, but if this is like 12 and this is 7 and this is like 5, you divide by 12, now you have this a whole bunch of ugly fractions, and as you continue to do your work, you'll end up with fractions everywhere, and it's a big pain in the butt. So try not to introduce fractions at all if possible, and if you do have to introduce them, try not to do it until the very last couple of steps. Okay, so normally what will happen is, let's say that this was 12, somewhere down here, one of these will probably be a 1 somewhere. So normally the first step that you want to take is to swap rows. That's normally the first thing to do, because if the first equation doesn't have a 1 in front, one of them normally will. And if it doesn't, okay, then use the third operation where you multiply one row and add it to another, and do it in a way so that you create a 1 and then swap your rows. That's going to be a lot easier to work with than dividing an entire row by some number. Okay, so that's kind of how you want to start. Either 1, swap, do a swap so that you have a 1 here, or add one row to another in some way so that you create a 1 and then do a swap. That's generally how you would want to start this, because you have a lot of options available at this point. Okay, so after you make this a 1, what you're going to do is you're going to make everything below it a 0. So in terms of equations, what we normally did is we had an equation here, and I said I want you to make all the variables under this one 0. So if this was like x, y, z, and there's nothing left, I would say make everything under your first equation, all the first entries, make all of those x's 0, right? So that's really the same thing that we're doing here. Okay? So that's what we're trying to do, is we make the first entry 1, and we zero out all of the things below it. So if this was, again, let's just say for posterity that this was x, y, and z, right? I only have one x, and all the x's and all the other equations are now gone, right? So there's only one x here. So what I do then is just like before, is I move to the next equation and the next variable. So before I just said, once we do that, make all the entries below it 0, but we actually want to make this 1 first because it makes it really easy for us to zero everything out, okay? So we call this a leading variable, right? It's the first non-zero entry. So when we come down, we now have a 0 entry. We make this leading variable now, right? Because we got a 0, and then this is now the leading variable because it's in the next row. We want to make it 1. Okay. Same thing. Once I have this as a 1, it's easy to get everything below it to be 0. Because let's say now that I have 1, let's say this is 7, and then the next one is 8, and the next one is -3. We saw before in the last section, it's very easy. If this is a 7, well, to get this to go away, I subtract from it 7 times this row, because 7 minus, turn this into a 7, it deletes. So from here, I take this number, multiply this by 7, and I take this minus 7 times this number. This number minus 7 times this number. It'll change all these values, but this first one will go to 0. And I do it for the next one, and the next one, and the next one. So if this is 5, let's say it's -5, I will add 5 times this row to this one to make this a 0, and so forth. We'll do an example, so don't worry. I know it's kind of abstract. We have done this before, but that's how it goes. So I make this 1, make everything below it 0. Next equation, I go in 1, right, to the next variable. I make it 1, and then make everything below it 0. Then I'm going to go to the next equation. I'm going to go to the first non-zero value, make it 1, make everything below it 0. And I'm going to keep on doing this until it is triangular. So triangular meaning I have my main diagonal, okay, where everything is 1. Everything above it is some number. I don't really care what it is at this point. And everything below is all zeros. Okay, so it looks like a triangle. So it's all zeros on the bottom triangle. Then I have a diagonal value of 1, or mostly 1s. Okay, there might be some zeros that end up popping in here. And then everything on top is just whatever number. Okay, so now what happens is it's triangular in form. This 1 equals, let's say 5. Well, that means I have 1 times z equals 5. So I can solve that. And then I go backwards and I substitute that into the next line. And then those 2 into the next line, and those 3 into the next line, and those 4 in the next line, up until I'm done, depending on what size matrix I have. Okay. So again, all the entries that are leading variables, these are called pivot positions. Okay, this is a pivot position, pivot position, pivot position. So those are very important to us later on. It's important that you hear this at some point so that we can talk about something later. Because based on the pivot positions, this tells us some information about our matrix. So again, once we introduce fractions into the system, they're not going to go away. So try not to divide something until the last possible point. Maybe you end up with 3 and 7 here. Well, that means 3 times z equals 7. So yeah, you're going to have to divide everything by 3. So you get z equals 7 over 3. And then as you back substitute, you're going to end up with some fractions. But that's fine because you kind of waited to the last possible second, which is ideally what we would want to do. Okay. So again, one more time, don't use fractions to the last possible minute. Okay. So let's go ahead and do an example. So we want to solve the following system. So as you see, I have a blank here. There's no x2. Your book might not give you a space. It might just say x1 plus x3 equals -3. You need to notice that there's no x2 value here for the second equation. So make sure that you leave yourself a space, or at least when you write your augmented matrix, take note that there's a missing value here and put that placeholder of 0 into your matrix. Okay, because again, remember, these are all the coefficients for my x1 variables, all the coefficients for the x2 variables. If there's one missing, then there's none there, right? And the x3 coefficients, and then my right hand side of the equation. So Remember what I want to do? I would like to get this number to be a 1. So if I divide this whole row by -4, this will be a 1, but then this will be a -1/2, this will be a +1/2, and this will be 5/2. There's fractions everywhere, because remember what ends up happening. I end up taking this row and adding it to other rows. So once there's fractions here, and then I start adding it to other rows to try to eliminate the values below it, I end up having fractions everywhere, and then it's a mess, and then it's not very fun at all. So an easier thing to do is let's swap rows. I already have a row that has a 1, so I can swap these out. You could also notice that this is a -4 in front and this is a 3. So I could say I'm going to take this row and I'm going to add this row to it, and that would make this a -1, and then I can change the sign on everything in the row, multiply the whole equation by -1, and then I have a 1 on top, and that's fine. Okay, but that's 2 steps to my 1 step where I could just swap the 2 rows. That's the easiest thing to do. So that's what we're going to do. I also want you to notice that all the numbers here are multiples of 2. So I could divide everything here by 2, and I'd have -2, 1, -1, 5, which is nice, but that doesn't do anything for me at the moment, right? So my goal right now is to make this a 1. So the easiest way to do that, I'm going to take row 1 and row 2 and swap them out. Okay, I'm just going to switch places. Easiest thing to do. So now that I have a 1 in the first position for the first equation, or first row, right? First row, first column is 1, right? You see why we call it A11? Because it's first row, first column value. See where they overlap? A11. So I want to get all the stuff below 0. So the first thing I'm going to do is I'm going to take this equation and I'm going to add to it 4 times this equation, or this row. So this will be 0. This will turn into 2 plus 4 times 0, so this stays as a 2. This will be -2 plus 4, so this will turn into 2. And this will be 10 plus -3 times 4, so this will be a -12. So this will turn into -2. Okay, so R2, my second row, becomes itself plus 4 times this one. So again, the first entry will be 0. This will stay at 2. This will be -2 plus 4. And this will be 10 minus 12. Okay. Here we go. So my first equation stays the same. It doesn't change. My second equation is just as we thought, right? So this turns into 0. This stays at 2. This turns into -2 plus 4, so it's a +2. This is 10 minus 12, so it's a -2. The first equation, last equation don't change. Okay. So I have a 1, I have a 0. I need the last row to have a 0 in its first place. So I'm going to take this row, right? So just think about what the notation will probably be. I need to take that row, R3. And what I'm going to do to it is I'm going to take R3 and I'm going to subtract 3 times R1. Okay, R3 is going to become row 3 minus 3 times the first row. So by design, this value will be a 0. Notice we have the exact same thing on the last entry here, so this will also be 0. This one, I will be subtracting a multiple of nothing. So this goes to 0, this goes to 0, this stays -1. This turns into -8 minus 3 times a -3, so that really turns into -8 plus 9. So this will be a +1. So I should have 0, -1, 0, +1. Okay, that's what we have left. So I now have 1, I have zeros below it. I would like to make this value into a 1, and I can do that by swapping the rows if I want to, or if you notice, everything here is a multiple of 2, so let's just go ahead and divide everything by 2. So R2 becomes half of R2. Okay, so 1, 1, -1 now, and then now that I have 1, all zeros below it, a 1, I need to make this a 0, so what I'll do is I'll just add these two together. So this turns into 0, this turns into 1, and this turns into 0. Okay, so I take R3 and it becomes R3 plus row 2. Okay, now we are triangular, right? My main diagonal has all ones. Everything below it is 0. And I'm pretty much done. So now I am in a triangular system. We call this row echelon form. I know that my x3 term is 0. And then I can substitute that back and back and back and back until I get my answer, right? So again, notice that our pivot positions run along the main diagonal. Okay, so we have what is called no free variables, meaning that this is a consistent system and has a solution. If there's a free variable, then there's infinite solutions. Okay, a free variable would be like if I had a row of zeros. If this was all zeros, then I would have a pivot here, but no pivot here, right? So my last variable would not have a pivot, so I'd have one free variable, one variable that could be basically anything, and that would result in infinite solutions. Okay, so we call this echelon form, okay, because it's triangular in form. All the I have all my pivots, right? All my pivot positions have a 1 in them. There's no free variables. There's no columns that do not have a pivot in them. To get into row echelon form, or REF is what it's called. Okay, so from here, once I'm in this triangular form, this row echelon form, in order to finish solving, I do back substitution, right? I know x3 is 0. x1 plus x2 is -1. Well, guess what? x3 is 0, so that means that x2 is -1. I also know that x3 is 0, so x1 is -3. So I actually have all of my answers here. Even just by looking at it, I can figure out what they are. But we can use our backward substitution in order to figure out what those answers are, like we did in the last section. Okay. For this example, however, instead of doing back substitution, we're going to do a backwards phase. Okay, so everything we just did is called a forward phase because we made this 1, then make everything below it 0, then make the next one 1, then make the next one 0. We're kind of moving in a forward direction. So what we're going to do is when we're done with our forward phase, we end up in a triangular form or reduced echelon form. And that's Gaussian elimination. We're going to move in a backwards phase where we do the same thing, but instead of doing it to the stuff below, starting from the first column, we start at the second column and we do the same thing but to the stuff above. All my values are already 1, so I don't have to worry about making them 1. So I'm going to try to make all the values above my last entry, my last column, not the right hand side, on the left hand side. I'm going to make this a 0 and this a 0. And then I would come over and I would try to make this a 0 if it's not already. Right? So what I'm doing is I did a forward phase, which results in this form, which is called Gaussian elimination, the process. Doing the backwards phase allows me to find all of my solutions just by looking at the system, and it's called Gauss-Jordan elimination. Okay. So again, what we're doing is we're going to turn our form, instead of reduced echelon form, we're going to return it to what's called reduced row echelon form. This is a little bit more powerful, just a little bit more work to find our answer and be able to look at it and say, okay, I know exactly what my answers are. Okay. So for Gauss-Jordan elimination, the first step is to use our Gaussian elimination, which is the forward phase, to put our augmented matrix into reduced echelon form, that triangular form we have, okay, like this. So what we're going to do is we're going to start at the last column that's on the on the left-hand side of the equal line, and we're going to make all the entries above the bottom one 0. Wrong direction. So we're going to begin the backwards phase. We start at our last pivot position and make all the entries above that position 0. So this is 0. We're going to add multiples of this to the other rows that we have and make all the entries above it 0. Then we'll move over to the next one and make all the values above it 0, and move to the next one and all the values above it 0, and the next one and all the values above it 0. Okay. Until we get only entries in the pivot positions. Everything else will be 0. Okay. We'll only have one number in every column on the left side and one number on the right hand side. So we'll have x1 equals whatever number's here, x2 equals whatever number's here, x3 equals whatever number's here, so forth and so forth. Okay. So for example, this is where we ended up. Okay. I will move my backwards phase. This is a 1, so it's going to be really easy. I'm going to take row 2 and I'm going to subtract row 1 from it. That will get this value to go away. This will stay the same. This one actually stays the same because it's -1 minus 0. Okay. So, or I guess I'm starting at the top. So R1 becomes R1 minus R3. So 1 minus 0 doesn't change. 0 minus 0 is not going to change. 1 minus 1 and -3 minus 0. So 1, 0, 0, -3. Next, I'll do it to the second row. R2 will become R2 minus R3 because there's a 1 here and a 1 here. And so 0 minus 0, 1 minus 0, 1 minus 1, -1 minus 0. And now I have my answers. 1 is -3. I'm sorry, x1 is -3, x2 is -1, and x3 is 0. So reduced row echelon form makes it very, very easy to identify what my answer is. It's just -3, -1, 0. If I leave it in my row echelon form, okay, this form, I have to do a little bit more math to finish finding out what my answers are. Okay, so that's the benefit. All right, so in our example, so let's say that we want to check our answer. Okay, how do we check our answer? Just like you would for anything else, right? This x1, this x2, and this x3 has to make my system of equations work for every single equation. So the value I got for x3, for x2, and x3, if I plug them into here, I should get out 10. If I plug those into here, I should get -3. If I plug those into here, I should get -8. Okay, so it should work for every single equation. If it fails for even one equation, then something's wrong, right? I messed up, or it's not a solution, right? So x1 is -3, x2 is -1, and 0. So here I'm going to have 12 minus 2, right? 12 minus 2 is 10. -3 and 0 will give me -3. -9 plus 1 plus 0, so -8. So it checks out. So if we were to reduce a matrix and it came into this form, for instance, right? So I was saying, what happens if we have a whole row of zeros, right? So for some reason, the third equation completely gets eliminated when I'm trying to make the entries below the second variable 0. Well, I know that x1 is -3 and x2 plus x3 is -1, but I have no idea what x3 is because there's no pivot position. There's no x3 equals a number. In this case, if this is what we had gone, right? This is what we actually had. So we call it a free variable. So the row that does not have a pivot, that's the free variable, right? So here there's a pivot, here there's a pivot, here there's not. So x3 is my free variable, meaning it can be anything. Okay, x1 is -3, x2 plus any number is -1, right? Because I don't know what x1 is, or I'm sorry, x2 is, so I can't really figure out what x3 is in this case either. So that would give me what's called a dependent system, right? That's when we have infinite solutions. What we had here was a consistent system, right? Or an independent system when we had one solution. So this is one solution. If it looks like this, that's infinite solutions. And remember, the only other case is no solutions. So if I had something like this, 0, 0 plus 0 plus 0, which is 0, equals 1, that's not true. 0 is not equal to 1. That would be an inconsistent system, and that would be no solution. So those are what you would, that's what you're looking for infinite solutions and zero solutions. For a single solution, it's very easy to tell what the answer looks like, okay? But sometimes you could come here and be like, well, what's my answer? There's infinite answers here, okay? if you have a false statement, right? My no variables equals 1. That is a false statement, so that is 0 solutions.